Good afternoon, this is Schweitzer. We're going to run a little video here on naming ionic compounds. So how do I know if a substance is an ionic compound? Alright, so first things first, you want to probably note that the first item is a metal. So it's pretty important to know where the metals are located on the periodic table. And with that said, this is the divider, little stair step. These are the metals over here, and these are the non-metals over here. So a metal and a non-metal probably would be the number one way that a general chemistry student would describe an ionic compound. Another way of looking at this is that it is a cation and an anion. So not all metals have to. Well, not all non-metals have to be cations and anions. So you'll notice here that this is a little grouping here. And this guy here is something you've definitely heard of this name, I'm thinking. The name of this substance, NO3, it has a -1 charge. This guy has a +1 charge. This is called nitrate. So the anions and even cations can exist in more than just a single individual. If it's a single individual, we call it a monatomic ion. Mono meaning one. If it has multiple atoms in here, we call it a polyatomic ion. And there's a bunch of these. We have a list of ones that are super common. Some years we would maybe have a little game to try and a little challenge, try and jam some of these into your memory, so that we can use them kind of like vocabulary in a foreign language. But without a shadow of a doubt, if at the end of the year I ask you what's NO3-1, you're going to spout off nitrate. That's how common these ions are, and we'll be using them a ton. You do have an ion sheet that's on the back of your workbook. Make sure as you're starting to get these things familiar that you are keeping that sheet close by. Alright, so how do I go about writing a formula for these? How do I go about giving them a name? Now, you'll find a name here is this is the process of giving names to things. Like we have a first name, a middle name, and a last name. Not all cultures have that, but this is a process for giving a substance a name. Alright, so let's go through how we write out a formula. Okay, now a formula literally is like a building list. Building, list. I mean, it's just a list of all your materials list. What are our rules? Okay, well, first of all, we have a cation and we have an anion always. That's ionic compound. So we list the cation first. We list, okay, the cation first. Okay. Second one is we charge balance. Now, I'll show what that means in a minute. All right. So here's an example. Okay. Now, aluminum chloride. Okay, so now one thing you might notice here, in the name, which will come up here in a moment here, the name does not give quantities. Okay, does not give quantities. So you're going to have to charge balance to get quantities. Okay, so let's do this. First of all, the cations first. Okay, aluminum. Go on your ion sheet or use the periodic table and get the common ion for this guy. It is aluminum with a +3 charge. Chloride only has a -3 charge, -1 charge. So then we want to balance these charges. You say, well, how many chlorides do I need to balance the one aluminum? And the answer is, I need 3 of them. So my new formula is AlCl3. Did it work? Well, I have a positive 3 charge, and I have a negative 1 times 3 is a negative 3. A negative 3 and a positive 3 equals 0, which is the charge on this substance. Okay. Ammonium sulfate. Okay, so, and ammonium is a polyatomic ion. Look on your ion sheet, very top. And I have sulfate, which is a -2 charge. Again, a polyatomic. Now, these guys work as wholes. How many ammoniums does it take to balance off the one sulfate? Well, I need 2 of them. So we do have this thing called the crisscross method. The crisscross method. And it's just a method by which you can, if you can't see that you need 2 of these, it should be apparent, but 2 goes here and the 1 goes here. Okay? So I need 2 of them. You'll see this crisscross method happen as I'm doing this. So how do I say that I need 2 of these? I mean, it's kind of big, right? So the way I write this out is like this. I take the ammonium, I don't want to change it at all, wrap it in parentheses, and I want 2 of them. And then I just need 1 of the sulfates, SO4, and like that. Typically we don't show the charges at the end because they cancel out. Okay. There you go. This is our example of the crisscross rule. The 2 came down here and the 1 went here. Just a shortcut way to charge balance these things. Alright, next guy, copper 2 phosphate. Okay, now why is that 2 there? That's because there's more than one version of copper. There's copper 2, which is copper plus 2. Remember, the name never ever gives quantities. So is this a quantity? No, it's a charge. It's the name of it. There is also copper 1. But I'm using copper 2 here. So Cu plus 2. Phosphate PO4 minus 3. Here's a great example of using this charge balance. The 3 goes here, and the 2 goes here. Anytime you have a polyatomic, you would need to wrap it in parentheses. The 2 otherwise would only count for the oxygen and not for the phosphate. So this is going to be Cu3 parentheses PO4 parentheses 2. Okay. Now, does this crisscross rule always work? I'm going to add one more down here to the video here, and it's going to be, let's go with calcium oxide. Okay. So, and I'm just going to type this out here, and I'll show it to you. Here's an example where again, this will be on your sheet here. So let's add one more in here, and I'm going to do calcium oxide. Alright, so does this work for us? Alright, let's grab our little ions sheet, or the periodic table should tell you what the charge is. This guy is calcium plus 2, and the oxygen is oxide, which is minus 2. Okay. And let's charge balance it. Well, that would give you Ca2O2. There's an issue with this, is that it needs to be what we call empirical. That these both need to be dropped down to CaO. Now, using the crisscross rule, you might get this. But if you do the original idea of charge balancing, you could say, well, this is minus 2. How many positive 2 will it take to balance it? The answer is just 1. 1 and 1, which would get you right to that guy. So the charge balance is something kids use a lot, but I really think of it, how much does it take to balance it? And I don't get stuck in this. This is sort of fictional. We don't want this. This would be marked wrong, having those 2's there. Okay? So that when you charge balance, those numbers have to be reduced down. I'm not referring to this 4 here. That 4 is part of the sulfate. I'm saying when you charge balance, those numbers that you're crisscrossing have to be to the most simplest form in the end. Alright, rules for giving these things names. Alright, this is pretty important. Alright, so not that difficult, but important. So the first thing to keep in mind, the name for this guy's never, ever, ever gives quantities. So what does it do? Well, it just gives the name of the cation and the name of the anion. And that's it. This is all it does. It never, ever, 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 ever gives quantities. So get your ion sheet out and let's just try a couple out. What's the name of that cation? That's ammonium. That guy is nitrate. Okay. This guy is aluminum. Now you'll find that aluminum is an ion. It's a positive 3 charge. I can uncrisscross this if I want to know my charges. Not that it matters right now. But you'll find that the anions get special names. The negative version of oxygen is called oxide. But we aren't giving any special names to the cations. Whether it's the ion or a regular metal, we just call it aluminum. Unless, of course, you live in Europe, they call it aluminium. But, alright, 3 hydroxides. Do I carry those 3 here? No, just call it aluminum. And this is called hydroxide. This is a little bit of a trick one. This has got more than one version of iron. So if I go iron oxide, there's going to be a little issue here because there's more than one type of iron. There's iron that is +2 and there's iron that is +3. So which one do we use here? Well, let's do a little inspection here. These are equaling charge. Oxygen always is a -2. This is therefore a +2 because look at how it charge balanced. And therefore I want to put a parentheses with a 2 here. And finished. Here's some practice. Some information here. The next page is just some practice. Pause the video. Try them on your own. Okay, now I'm going to start going through some examples. You should have already tried these. I'm just going to flip back and forth between the names and the formulas. This is just magnesium chloride. This is aluminum sulfate. Aluminum with a +3 charge. Sulfate, SO4 with a -2 charge. Charge balance. I get aluminum with a 3 here. And a 2 here. 2, because the 2 goes there. The 3 goes here. I do have to wrap this in parentheses because it's a polyatomic. SO4, parentheses, 3. Copper 2 acetate. Okay. Cu, parentheses, C2H3O2, parentheses, 2. This was a +2 charge. This is a -1. When you get better at it, you can just jump right into it. Calcium carbonate, +2, -2. Alright, so this is just the name of these guys. Calcium carbonate. This is iron. The 2's here. That's not part of the hydroxide. That's part of the charge balancing. This is a +2. This is a -1. Iron Roman numeral 2. Hydroxide. And this guy's copper 2 sulfate. So it's copper with a +2 charge. And sulfate, SO4 -2. So it's just going to be CuSO4. Now the next page is a little bit more about how we actually get these. How does this happen, like on a molecular level? How do we get this thing to form? Well, in this case, the way this happens, and you know, why are our ionic compounds charge balanced? Why is it always equals 0? Well, it turns out it appears that the protons and the electrons in nature are pretty much equal. And some kids, I tell them that if you were on Earth someplace, and you see a pile of dirt someplace, then likely there's going to be a hole someplace else. And the hole will fill it back up. That's kind of what we have here. Every time we have a negative created, there was a positive also created. Every time you have a pile, you have a hole. So, and they should match each other. But on an atomic level, how are they made? Well, it turns out that an aluminum metal, which typically has 13 protons, not typically has, and 13 electrons. Now this is 13 protons and 10 electrons. And here are the 3 electrons it lost. Well, then each chlorine, here's a Lewis dot, each of them picks up 1 electron, and I need 3 of them to make this work. Each of them grabbing 1 electron. And we have this. Therefore, I get 1 positive 3 and 3 negatives, and I get Cu, or Al, Cl3. Al with a positive 3 charge. I get these chlorides, and they simply attract to each other because they're opposite charge. This guy here, magnesium, okay, has how many do we have here? Well, it's got a positive 2 charge. There's one of them for a positive 2 charge. Oxygen, there's one of them for a minus 2 charge, giving me minus 2. So I'm just kind of showing you how that works. If you want to write the equation out, you can. Here's another example. Again, I'm just going to briefly run through these because I don't want to go through it too much, but the metal's going to oxidize and the nitrogen's going to get reduced. So the barium is going from barium to barium plus 2, and then here's the 2 electrons. This is the idea of losing electrons. That's what we call oxidation. If you gain electrons, which is what this guy's going to do, then we call it reduction. It's weird, I know, but nitrogen, okay, and in this case, you can keep it N2 if you'd like, or just plain N, depends on how complicated you want to make it, will form N-3, that's the standard charge of these guys, so I'll have to add 3 electrons. This process runs, in order to get the same loss as gained, this one has to run 3 times, and this one has to run 2 times. That gives me 6 electrons, 2 of these, and 3, and 6. Hence I get this right here. 3 bariums, 3 bariums, 2 nitrogens, 2 nitrogens. So our overall formula would be 3Ba plus 2 nitrogens, or 1 and 2, if it comes in pairs, it's shown here, will yield barium 3 nitride 2. And that's how we get that formula. This is a little side note, just mentioning that some elements do come in pairs in nature, and just so you know where that came from.